Like we motivate the curvature. So what's going on? So if you're traveling along a space curve like this, okay? So basically, when you talk about the curvature, this is how fast, right? How sharp is how sharp is the roll, right? So basically, if you think about the location at this point, when you're driving on the road, so you are pointing at this direction, right? So this is the unit's tangent direction along the curve that you can think about. But then at another point, your direction has changed already, right? So this between these two black points, this direction doesn't change very drastically. But if you move along the curve, you will see, okay, the next point may be right here, and then the direction has changed from pointing towards the right to pointing towards the left, right? That's drastically change. And it could be something also really significantly changed back to pointing towards the right, right? So certainly when we talk about the curvature, we want to measure how fast, right? How rapidly you are changing your direction. So even if you are looking at only the unit tangent direction, still you want to know the rate of change. But then, like I mentioned earlier, if you parameterize your curve differently, so if you travel faster, then the direction change will be more aggressive. But if you travel really slow, like climbing on the highway, then at any time point, it seems like you're not really changing the direction at all. But but you're driving, let's say, on a motorcycle, that direction change may be drastically. So the curvature that we define is only with respect to the arc length, not really with respect to the parameterization. So here, the curvature of a curve RT at a given point is the measure of how quickly the curve changes direction at the point. Formally, it is the magnitude of the instantaneous rate of change of the unit tangent direction, the cap T, unit tangent direction, cap T, with respect to the arc length. Little arc length function, and we call little s. So here, to put it down in your equation, this curvature is always denoted as kappa. And then it looks like a K, but it's more curly, yes. So it's going to be D. So the rate of change of the unit tangent direction with respect to the arc length, okay, and we take the magnitude. remark. So notice that basically we want to reparameterize everything in terms of S. That's what we are doing here. Okay. So basically, if you think about the rate of change of the unit tangent direction, here we are doing the intermediate variable as S. Okay. So it's going to be ds dt ds times ds d little t. So this is the chain rule that we are familiar with. Right. And here, this t is reparameterized by little s of t. So from the equation above, if we divide both sides by ds dt right here, and then we will be able to get another formula. Yeah, so let me quickly write the formula down. Oh, by the way, the exam will cover everything up to the Laplace function. So basically everything until 14.4. Okay. So curvature is not going to be covered. So here we're just doing both sides for the division of the d capital dt over ds dt. So if you recall, the top, of course, is the rate of change of the unit tangent direction. But the bottom is what? The bottom is the magnitude of our prime. Okay. So recall, this little s is defined as the interval from 0 to t of r prime little u. Yeah, the equation. So yeah, let me quickly write down the equation at our end of it. So hence, kappa is you have t ds taking the magnitude, which is this taking the magnitude. Okay. So it's the magnitude of t cap t prime over the magnitude of little r prime. Okay. So this is another formula I want to put in the notes. So basically, here, the letter we use for curvature is kappa. And then, if you think about the definition, is that okay? We have the unit tangent direction. When you're traveling along the space curve, your direction will just change with respect to the path you're going, right? And then you want to get the rate of change when you are just walking along the space curve in terms of arc length, right? So it's going to be the rate of change, instantaneous rate of change of your direction with respect to the increment of arc length. And then we notice that we are able to somehow reparameterize and just use the chain rule to eventually calculate the curvature by the rate of by the magnitude of cap t prime, which is essentially the rate of change of the unit tangent direction, and we divide by r prime, which is the rate of change of the arc length. Okay. So remark. Here, of course, if you're looking at the denominator, you always want the denominator to be non-zero. Okay, so we need r prime to be a non-zero vector function, and t prime the tangent, the unit tangent direction must have a derivative, okay? To be defined. For curvature, we will focus on those nice curves, okay? Focus on curves such that the tangent direction is continuous and differentiable. And they are actually called smooth curves. So of course, the thing is, cap t, okay, cap t directly relates to the tangent direction. Okay, so this is a normalized tangent direction, so it must be differentiable. Okay, that's something critical here. Example. We want to find the curvature of the space curve R of t. That is actually the unit, well, the circle with radius r within the xy plane. So r cosine t I plus r sine t j. Okay, so cap I is actually just the radius of the circle. And we want to know the curvature at any time, at the time point t equal to 0. Here, cap I is a positive constant. So if you think about the curve is just the circle, okay? And here we are studying it in R3. So to quickly illustrate the geometry, so basically we are having the right-handed axis, x, y, z. But then we only have I and j, so that's it within the xy plane. And then we just have a circle, and the center is 0, 0, 0. So that's actually the circle right here. Right. Circle of radius kappa. So somehow you can imagine that basically when we talk about curvature, this is just you're walking along the red curve, and that basically this is you increase your plans by, let's say, 1 unit, and then how much has your direction changed, right? So if the radius is huge, then the curvature is not as big as if your radius is small, okay? So the smaller radius may give you a larger curvature. So now let's just do the computations to see if that's actually the case. So we have R, so we want to calculate R prime, of course. So it's component-wise derivative. Okay, so cap R is a constant, cosine gives you a negative sign, so negative R sine t in front of I, and then sine gives you a cosine, so plus cosine t j. Okay. And then we realize that for cap t we need to. So let's quickly look at the formula. So we want cap t, and we even want to differentiate that. Okay, so cap t is what? Cap t is the normalized vector unit tangent direction. Okay, so we want to calculate the magnitude of little r prime, and then we do the division. So here, this is fortunate that we're under the square root, but we have a Pythagorean theorem. So the first component squared is r squared sine squared. The second component squared is r squared cosine squared. Okay, and if you recall, sine squared plus cosine squared is equal to 1 by Pythagorean theorem. So we have under the square root of kappa r squared. And we also know that since kappa r is positive, we know that can directly take the square root and we get just kappa r. Okay. So we know that the magnitude of r prime is a constant, so now we can just normalize. So the unit tangent direction is gonna be little r prime over its magnitude. Okay. So you see, we're just dividing by kappa r. So we get rid of kappa r in little r prime. So just negative sine I plus cosine j. Okay. And we see, okay, this is definitely a unit vector because the component squared gives you 1 by Pythagorean theorem. Okay. And then we just need to calculate the derivative of this for the numerator of the curvature. So, and turns out it's not really hard because now components are just trig functions. Okay, so negative sign, so the derivative sign gives a cosine, so it's negative cosine I. And the cosine gives you negative sine. So and if you recall, in the curvature formula, we have the magnitude of t prime. Okay. So we just take the magnitude, and you see, this is again the Pythagorean theorem tells you that the magnitude here is 1. Okay, but this is still a unit vector, which is nice. So the magnitude is the square of the first component plus the square of the second component. And that's a 1 again. So it's good. If that's all good, then we just finally just apply formula, right? So at t equals 0, we have kappa equals to basically it's cap t prime over little r prime evaluated at t equals 0. And let's see. So basically, cap t prime is 1, and little r prime is what we calculate here. It's actually a constant also. So we have 1 over r and evaluated at t equals 0. But we do know that here, this expression does not relate to t at all. So it's a constant. So basically, it just means what? It just means no matter where you're at on this circle, okay, regardless of the location, regardless of the time t, the parameter, the curvature is always the same thing. Okay? It's just 1 over epsilon. Right. So at any point on the circle, the curvature is the same. So we mark. Indeed. At any point with parameter t, on the above curve, on the above circle of radius kappa r, the curvature is always 1 over kappa. Okay. So this is really intuitive in the sense that for a circle is symmetric with respect to its center. Okay. Okay, now let's look at another example. So the example we have seen just now is a direct application of the formula for curvature that's represented right here. Okay. But in some cases, the numerator cap T prime may not be so easy to calculate. So let's see. Even if you have relatively simple vector function, that's still possible, okay? Because when you think about cap T, it's always normalized, right? And if the denominator, the magnitude of R prime is getting complicated, then cap T is complicated, and cap T prime is also complicated. So let's see. So if we have a vector function that's in terms of t squared, t cubed as the components, we want to find the curvature as a function of the parameter. About t at general point with parameter little t at a general point. So basically, let's see. Let's follow the process. So little r, this is just a polynomial. It just has have polynomial entries. So it shouldn't be very complicated when you do the tangent direction. So component wise derivative, right? So r prime is gonna give you t gives you just 1, t squared gives you 2t. T cubed is gonna be 3t squared. Just these are all just the power rules of the derivatives. And now remember that we have the magnitude of R prime that we need to calculate. So that's a radical already. The square root of what the sum of the component squared. That's 1 plus 2t gives you 4t squared plus 3t squared gives you 9t to the 4. Okay. So this appears right here, and also it appears in cap T at the unit tangent direction. So now the unit tangent direction becomes a little ugly because this is a division. And then we're just introducing a denominator at every component. So we can see, okay, we have R prime is this 1, 2t, 3t squared. And we are dividing every component by this radical. So it's kind of ugly. We have 3t squared at the last component. So the thing here is that it's not only tedious to write out the denominators, but also now if you consider calculating cap T prime, okay? If you calculate the derivative of this, and also you want to take the magnitude again, so that's going to be kind of complicated. So it may not be so bad if you're just taking the derivative because it's just quotient rule, right? But then here is we don't really want to calculate explicitly because it's just gonna get more and more complicated. So let me just leave the blanks for the component-wise derivatives. So it may not be so bad, because we have the quotient rule, but it's just, complicated. But still, the next step is what? The next step is the magnitude of the possibly complicated components. So we still need to calculate this. And finally, we just do the division in the curvature formula. Okay, so this may be highly complicated. Okay, so in this example, you see, we start with what? We started with a curve that is having just the polynomial expressions as components, right? And when we get to more complicated curves, this process may be highly complicated. Okay, so this set phase, some kind of choice instead of calculating the explicitly components. So here the remark is motivating as another formula for the curvature. Instead of using formula where kappa of t is T prime over little r prime, both in magnitudes, it is sometimes preferred to have a formula that does not involve T prime. Okay. So here the problem is the T prime is already a complicated fractional kind of curve component wise. Okay. So if you take the magnitude of that, it's even more complicated. Okay. So that's something we want to avoid. And here comes that formula. So it's a theorem that just says kappa t, the curvature at any point is calculated by division as follows. So it's the magnitude of r prime crossing with r double prime. Okay. The tangent direction plus the second derivative direction. And we take the magnitude. Whole thing over little r prime, the magnitude to the 3. So this is another formula that's relatively speaking kind of powerful when cap t prime is complicated. Okay. But well, as in the previous example, cap t is really simple, so we don't really have to utilize this formula here. Okay. But just in case cap t is something complicated and the derivative is more complicated, and then the magnitude of that is even more messy, then we use this formula. So let's quickly look at the example that we started. So let's utilize the formula here to calculate that curve t squared t cubed. Okay. So let's do this. So here we see, okay, we only need to calculate r prime, r double prime, right? So we have already calculated r prime as 1, 2t, 3t squared. And here we just do the derivative again, component wise. So 1 gives you 0, 2t gives you 2, 3t squared gives you 6t. Okay. So now, okay, the next step here is that we need to do the cross. And the cross is not really complicated because it doesn't involve any fraction. Untouched. prime crossing R double prime. So let's just do it by definition. So ijk in the first row. And then the second row is R prime, so it's 1, 2t, 3t squared. The third row is 0 to 6t. Let's just keep the formula there in the screen. So, okay, so let's quickly be reminded about the process, okay? So for I, it's gonna be the elimination of first row, first column, and then we have two by two order 2 determinant, right? That's in front of I. So it's 2t, 3t squared, 2, 6t. This determinant in front of I minus the 2 by 2 that you get when you eliminate the first row, second column. Okay, so that's 1, 3t squared, 0, 6t. Right? So always remember, very important, that this is a negative sign in front of the order 2 determinant in front of j. Plus. In front of k, we just eliminate the first row, third column. That gives you 1, 2t, 0, 2. That's the remainder for k. Okay. Yeah, I can still keep this here. So I can calculate the components now. So for order 2, it's always the diagonal. So the diagonal, remember, don't confuse with this. This is the off diagonal. Okay. So the diagonal is along. The diagonal is first row, first column. Then second row, second column, and the third row, third column. So that's the diagonal in the matrices. So 2t times 6t, that's 12t squared, minus the off diagonal multiply is 6t squared. So that's a 6t squared I. And then for j, we have a negative sign, but the diagonal is a 6t, the off diagonal is a 0, right? So minus 6t j. And then plus, now we have what? We have 2. And the thing here is it shouldn't be difficult to check your answer. Okay, so you use the result to dot with this. So 6t squared minus 12t squared plus 6t squared. Okay, so that's definitely orthogonal. And then if you dot with the row beneath, that's going to be what? Negative 12t plus 12t. Yeah, exactly. Always double check. Okay. And we're almost done. So here we know the cross within the formula at the top, we just need to take the magnitude, right? And then for the denominator, it's just R prime, we take the magnitude and then raise it to the 3. Okay? So we have directly write out the answer. So for curvature, it's going to be R prime crossing double prime over R prime, taking the magnitude to the 3. So although every magnitude here is a complicated radical, but we don't really need to simplify any further. So 6t squared, that's first component squared, and then plus 6t squared, then plus 2 squared. Now, well, so we don't really need to do that. I just want to put 4 here, right? So that's the radical for the numerator, and for the denominator, it's going to be the square root of so R prime, so it's going to be 1 plus. Then we have calculated, right? So 4t squared plus 9t to the 4. So this radical we raise to the power 3. So you see here we don't. So here we don't really have to calculate cap t, the unit tangent direction, and then we avoided the complicated magnitude that's in the numerator of the original kappa formula. So that's good. And this is in a way it's sort of a review, right, for cross and for component-wise derivatives. Okay, so now we see that this formula is powerful at least within this example. So let's do the proof. So actually the proof is not so complicated because we actually have learned the things that are necessary. Okay, recall that we know the definition of kappa is F T prime taking the magnitude over R prime, little r prime, taking the magnitude, right? And here we need to prove another formula. So what do we need? We actually need to show that the right-hand side here equals to this. Okay. So as long as we establish this relationship, then we're done. Okay. And here we simplify the notation by omitting the argument t. So that will make it simpler. We want to prove that cap t prime over little r prime. So this is the right hand side of the original equation. Okay, so we wanted to equal to the right hand side of the new equation, which is little r prime crossing little r double prime over little r prime the magnitude to 3. Okay, so here we just omit the argument t and the brackets. Okay. And then, of course, we just rationalize everything. Well, basically, you see, we have a common denominator r prime, and on the right hand side we have that power to the 3. Okay, so here we just get rid of the denominators. So equivalently, we need to prove that basically if you multiply both sides by r prime, the magnitude to the 3, then we just need to show that r prime crossing r double prime. This one has the magnitude of little r prime magnitude squared times the magnitude of cap t prime. Okay. So this is what we need to show. Okay. And as long as this is proved, then we're done. Okay. Now, recall. So r prime, the magnitude, we know what this is. Okay. So this is exactly the rate of change of the arclength, right, as a function. So instead of proving this formula, we just want to replace r prime, the magnitude, okay, by ds dt, the rate of change of arclength. We need to show that the cross has the magnitude to be ds dt squared times the magnitude of cap t prime. So this is the equation which we call star. Okay. So within this screen, we see that if we want to prove the formula that we want, essentially we just need to prove this. Okay. If this is established, then everything is good. All right. Now let's prove this. So we wrote this dsdt here for a reason. Okay, so this is a scalar function, right? And actually we know how it's related to t prime. Well, we know how it relates to t and r prime, right? Because t is a unit tangent direction. Okay, so since T is the unit tangent direction, which is what? Which is r prime over its magnitude. And here on the right hand side, or excuse me, on the left hand side of the equation star, we will have what? We have r prime, right? So here we're just trying to express r prime by t. And of course, we know that r prime, the magnitude is ds dt, so this is the same formula that we have seen above. So we can express theta r prime by ds dt, the scalar function times the direction. Okay? So r prime. So r prime is the tangent direction. Okay? So it is some number multiplying by the unit tangent direction. Okay? So that's something that's for sure. And now what do? This is a product of a scalar function and a vector function, right? And here we just we want one more time of derivative, and it will give us double prime, and that's product rule. Okay. So a little bit more descriptive words. Taking derivative on both sides. Okay. Taking derivative dt on both sides. So it's the derivative of the first times the second plus the first times the derivative of the second, right? So this equals to ds dt. This is the scalar function times the vector function. Whole thing taking the derivative. This is the first the derivative first. This is the second derivative of the arc length multiplying by t plus the first times the derivative of the second. Okay. So here, this notation is the Leibniz notation for actually just theta s taking the second derivative. Okay. All right. Now let's do the cross. Okay, so we have r prime, we have a double prime, and we see t prime. Okay, so we're getting there. Cross. So let's write out this vectors. So ds dt times cap t, that's our r prime. We want to cross with this vector here. So although I'm copying and pasting, but here something we need to know. So when we are so here this is a sum in the second part of the cross, right? And this is something we can distribute. Okay, so this is a cross with the first vector plus the cross with the second vector. And at the same time, you notice that t cross t. So cap t crossing with itself is just going to give you a zero vector. Okay, so that's very nice. And also we do know something about the relationship between t and t prime. We know that they are orthogonal. Okay? So that's something very nice. So let's do the distribution. So here we have ds dt times the second derivative of arc length, and then we have t cross t plus in front of t cross t prime, that's actually what? That's actually ds dt whole thing squared, right? We have 2 copies of that. And let's put it in the bracket. Okay. So, okay, so here, although this part is kind of complicated, but we know what we know. T cross T itself is going to give you. It's going to give you something interesting, which is what a vector crossing with itself gives you zero vector. Okay. So that's going to be gone. Okay, so this thing that does not really occur in the calculation. So this directly becomes now ds dt squared. And then we need to be concerned about the magnitude of t cross t prime. Okay. And it's actually really close because if you think about it, we want to show the magnitude of the thing right here is gonna be what? It's gonna be ds dt squared. Well, that's the same here, right? We just want to show that the magnitude of the cross t cross t prime is essentially the magnitude of t prime. And that's actually not difficult. So hence, let's take the magnitude on both sides. R prime crossing a double prime, the magnitude of this. Okay, so notice when we take the magnitude of the right hand side right here, the function at the front is a scalar function and it's positive, right? So when we take the magnitude of the whole thing, we can drag the scalar function out. So it's going to be ds dt squared. So this is a scalar function. It will not really affect the magnitude, right? And then the magnitude of t crossing with t prime. So this is actually not difficult because let me put it in red. So by definition, the magnitude of the cross is what? It's the vector, the magnitude of the first vector multiplying by the magnitude of the second vector multiplying by sine of the angle cut between the vectors, right? And what do you know about the angle cut between these two vectors?
It's 90 degrees.
90 degrees, exactly. So that's very good. So this is parallel 2, okay, sine parallel 2. Recall, t starting with t prime is 0, always, okay? So that's something we have proved a little bit earlier. So what do we know? We know this sine of pi over 2, this is 1. Okay, this is 1. We know the magnitude of t, the unit tangent direction, that's also a 1. Okay. So now we have 1 times the magnitude of t prime times 1. Okay. So this is exactly ds dt squared times the magnitude of t prime. Okay. And that equation star is now proved. So that tells you the formula that we want to derive is indeed true. Okay. So thus equation star holds, and with it, they call it what? A tombstone, right? QED. So now you see, okay, this this fact that we derived earlier actually helps. Okay, so okay, we still have some time. So let's talk about the normal and binormal vectors. Okay. So we were talking about the tangent direction and then the curvature. So now normal vectors and binormal vectors. So basically, let's quickly sketch a space curve again. And here, let's think about what we have mentioned for the derivative, the tangent direction and normal direction. So, we haven't actually mentioned what the normal direction is, but for the unit tangent direction, it's always the vector that's along the curve that you travel, right? Along the direction of the curve at any point. So these are the unit tangent directions. Okay. And then if you recall, we also mentioned that, so these are cap T. That's cap T in red, right? But then we also mentioned that if we think about the rate of change of cap T, it's actually perpendicular to these red vectors. So here, this is kind of like if you're just traveling along the curve, this is what turning towards the right, right? So it's slightly turning to the right, and then more drastically turning to the right, and then slightly. So the vector T prime, cap T prime, is actually just pointing downwards, right? But we want to get the things defined nicely. So think about the definition of the curvature. So curvature kappa T is, if you think about the definition, then we started with is the rate of change of the unit tangent direction with respect to arc length, and then we take the magnitude, right? So now, this means what? This means for the rate of change of the tangent direction with respect to the arc length, this can be represented by this scalar right above multiplying by the unit direction. The unit vector along the direction. So if we want to get the direction, we simply isolate the magnitude in the front, okay? So that's the thing that we have learned about the vector, okay? So we always isolate the direction as a unit vector, and then the magnitude here is exactly the curvature at any point, right? So that's our definition here. So the magnitude here is something that we call as curvature, right? So what about the vector here? Okay. So the vector here is the normal vector, and the name is special. It's called principal unit normal vector. Okay. So if you recall, the unit tangent direction is just a unit tangent direction, right? But here we have a principal in front of the unit normal vector. And this is denoted as cap n of t, which is defined by the equation as the direction on the right hand side. So it's cap t, cap t ds over its magnitude. Okay. So if you think about this definition, it definitely looks complicated in the sense that it's in terms of arc length, right? Here, if you think about the reparameterization that we have done earlier, so if we just reparameterize everything in terms of the time variable t, then it's still going to be fine. So remark. So n of t equals to, so let's write it again, so dst. So basically, so this is the formula that we have. If we This is the equation that we start with, the definition, right? So now, think about the chain rule. So dt ds, you can represent it as dt little t times dt ds. So dt ds is a scalar function. And you can do the same for the denominator. Okay. And here the point is, this is a scalar function, this is a scalar function, and in fact, dSdt is what? dSdt is the rate of change of our hands, which is positive, right? So dTds is also positive. Okay. So there's a bracket that I'm gonna include a little bit later, but here, let me quickly put down the next equation for this principal unit normal vector. This is actually, this is cap T prime, right? That's the magnitude of cap T prime. So let me write it down. Cap T prime over its magnitude. Okay. So this is another formula. So we know that when you define the unit tangent direction, it's cap T, which is the normalized vector of R prime, right? The tangent direction, you normalize it, you will get the tangent, the unit tangent vector. And then now we see that we can just take the derivative of cap T and then we normalize it, okay? That will give us the principal unit normal vector. And we know that actually T and T prime, they are perpendicular to each other. So it's natural that you can cross these two vectors and get a third unit vector. Okay? We know that T and N are perpendicular. Since T dot T prime is 0. And so this is something we have done. Let me see. In 14.2. Okay. Hence, we can introduce the unit binomial vector so we just use cap B to denote the cross between T and N. So and of course, this is a unit vector. Because if you think about it, the magnitude of B is what? So it's the magnitude of T times the magnitude of N times the sine of the angle between T and N, right? From T to N. But then you know that they're perpendicular, so this angle is actually covered too. Okay. So you know that T is a unit vector, N is another unit vector, and sine of pi over 2 is 1, so it's exactly 1. So now actually we see that we have three vectors that they're all perpendicular to each other. And that's actually really similar to the standard basis, right? IJK, right? This tells you, okay, at any point on the curve, you are able to define these three directions. So remark. So basically, if you think about the standard base, is really similar. The standard base is IJK. You know that this is a coordinate system that's right-handed, right? And now if you think about T, N, and B, these three vectors, that's exactly the same idea. So if you start with T and N like this, and then B is the cross of T crossing N. So B is exactly the direction that's in place of K on the left hand side, right? This is exactly equals N. Okay. So this kind of coordinate system we can construct at any time point T, right? So basically, when you're traveling along the curve, you're able to set up this kind of coordinate system. So squat D. So let's make the curve relatively simple. The space curve like this. Okay. So in this situation, for whatever point that you pick on along the curve, that's at the black point. So if you basically if you think about it, the tangent direction is the direction that's along the direction of your space curve, right? And then we make it a unit vector, so that's cap T. And now if you think about T prime is what? T prime is the way that you turn, right? So it's the way that you change the direction, cap T. So that's T prime, which is perpendicular to our red vector here. So yeah, I'm gonna move the Z coordinate here. So so T prime is this direction, but then we normalize it, that will give us what? That will give us N. Right? And now if you think about cap B is actually the one that's the cross between T and N, right? So now if you think about the right-handed rule, so okay, so we are just going the direction. So we're just going so our hand is going along the direction of cap T, pointing towards the right, like this. And then we can bend our fingers along the direction of N, which is like, we're kind of turning left slightly, right? And then B is just gonna be pointing towards ourselves. And let me just draw the unit vector B like this. Okay. So it's gonna be perpendicular to both T and N. Right? But if you really want to visualize it in a three-dimensional space, then that's actually just gonna point out from the monitor point of view. Okay. So we can introduce a T and B coordinate system. And this can be constructed at any point along the curve, right? As long as you can differentiate your tangent direction to get the principal normal direction. Right. So here, then we have three terminologies for the planes. Okay. So this is what's called the oscillating plane. That's the TN plane. And then there's the normal plane. Which is the MV plane. So basically, you can think about t and n. So t is the way that the direction that you're traveling along, right? N is the way that you're turning. And now, basically, the plane Bn is actually entirely perpendicular to the direction they're traveling, right? So that's normal plane. And finally, there's a rectilinear plane. That's the TB plane. Example. So you see, let's look at that helix that we have seen earlier. So the vector function is cosine of t, sine of t, right? So basically here, we just need to realize that we need to get t first, which is a unit tangent direction. And then we make the rate of change and we normalize that again. Okay, and finally for b, we just cross, okay? So that's just it's gonna be standard process for differentiations. So the tangent direction is what? So cosine, the derivative is negative sine. Sine gives you cosine, t gives you 1, right? And then the unit tangent direction is gonna be r prime being normalized. So we just have the vector function and we divide by the magnitude. So the magnitude of this is actually pretty simple that we have seen already. So the squares of the components added up. And we know that so sine squared plus cosine squared is actually 1, right? So it's Pythagorean theorem. So in the denominator, we actually have what? Have square root 2. Right? So here we just component wise divide by square root 2. So negative sine t over square root 2, cosine t over square root 2. I need a little bit more space, so let me move it. Finally, we have 1 over square root 2. To make sure that the vector right here is a unit vector, right? So it's good. That's standard, right? And now, so cap t prime. So if we differentiate, we will expect to get a vector that's perpendicular to t. But let's see. So sine gives you cosine, so we have negative cosine t over square root 2. Cosine gives you a negative sine, the derivative square root 2. And finally, the last component is a 0 because it's a constant taking the derivative. And you can see, okay, this vector is has an even easier magnitude, right? Because if you think about it, negative cosine, negative sine, 0 will be the unit vector along this direction. But of course, we can do this really systematically. So Fn is going to be t prime over its magnitude. Negative cosine t, negative sine t, over square root 2. And okay, for the magnitude of this, we just sum the squares of the components. Okay? So it's going to be cosine squared over 2 plus sine squared over 2 plus a 0. And you see, okay, we have 1/2 within the square root, okay? So this division that you do, so you will cancel out the denominators. So this is negative cosine t, negative sine t, 0. So just like a vector on the unit circle. That's good. So finally, the binary vector is just going to be the cross. Okay? So cap B is cap T cross cap N. So by definition, we're going to put down T and N as the second and third row. Okay? So here, this is not going to be complicated. So we just carry out the calculation. But that I'm going to leave for you guys to check. So you should get a null vector. Okay? So which is 1/2 times sine t negative cosine t 1. Okay? And you can see this vector, the format is really similar to the tangent direction, okay? But they are force perpendicular. If you do the dots, you will have negative 1/2, negative 1/2, and then what? Oh, excuse me, negative 1/2 sine squared, negative 1/2 cosine squared, and plus 1/2. Okay. And if you, of course, if you dot with this vector, it's also going to give you a 0. Right. So that's pretty much all we have to discuss about the space curves. So in this section, we have two formulas for the curvature, but I would just like to mention that so here in this helix example, then T prime is not really complicated, so it's always easier if you just use the first equation for the curvature to calculate. Okay, but if T prime is looks complicated when you're doing the calculation, then you can use the other formula that you just cross R prime and R double prime and then divide by the magnitude of R prime to the 3. Okay, so there are two formulas of curvature. So there's always a kind of freedom of choice, which is always making this kind of Calc 3 questions harder in a sense.